Welcome to the satellite communication course. Now we'll see here a space diversity. In a space diversity, we have the two different Earth station there. So means what? In some of the Earth station nearer to the Earth station, there is a rain, and here for this Earth station, there is no rain. When a satellite transmits a signal, so this signal get affected because of the rain. Because in this region there is a rain, but in this region there is no rain. So in a space diversity, what we have to do? We have these two different Earth stations are there. So these two different Earth station will receive a signal, and that because of the train, okay, at this, because of this particular Earth station, that will receive the signal. There may be a delay because of the train there, or we can say that there may be a that attenuation of this particular signal. So now here, if supposed to be there is no rain, so both the satellite receive the same signal level. But if some of the one of the Earth station, sorry, both the Earth station will receive the same signal. If one of the Earth station is in the region of the rainfall region, so in that case, some of the signal having the different level and this signal have the different level. So means these two different those signals have the different level because of that attenuation. So in a space diversity, what we have to do, we need to process the two signals. Okay. In the space diversity, what we have to do, we have the two receiver here. This one is another receiver, this one is another receiver here. Earth station A, Earth station B. And then we use a diversity processor. And the diversity processor will consider select any one of the signal, and then using that, that will be transmitted to the particular band of operation. Okay, particular operation. Generally in a space diversity, the two different Earth stations are far away from this, but these two Earth stations, they are connected to the one of the center. So that is nothing but a diversity processing unit. Means whichever the signal received by these two Earth stations, that will be taken to the diversity processing center. Then diversity processing center compare the two Earth station signal or two received signal and select that whichever the signal is better now in terms of the signal strength. And then that selected signal will be used for the reception there. And that is nothing but a space diversity. So another option is about instead of a space diversity, we have the another option is about the orbit diversity. So in the space diversity, what happens? So we need to use a two Earth station or we need to use a two Earth terminal there. So in a orbit diversity, we need to use instead of a single satellite, we need to use a two satellite in the orbit, and they are separated between them some particular distance. So in a Earth station, okay, whichever the we have the ground terminal or we have the receiver Earth station, that receiver will receive the signal from the two satellite. Means Earth station will receive the signal from the two satellite because these two satellites are separated in the same orbit. Okay, because two that is nothing but a orbit diversity. So the Earth station will receive the signal from the two satellite because of whatever the satellite present in the one there will be a separation between the two satellite. So that's why the When a signal is received by the Earth station from one Earth satellite and from another satellite, because there is a path difference now. There may be a slant angles, okay, because of that path changes there. So that's why there may be a diversity in the received signal. And that whatever the signal, we can say that whichever the received signal by the satellite there from this transmitting from the satellite and received by this Earth station, that signal is that will be affected less as compared to this orbit space diversity there, because of that a slanting there, slanting path, or they have a slant angle there. But what happened here, because these are the two satellites are transmitting the signal, so at the Earth station, so on the ground, so it requires a two different antennas on the Earth station. So one antenna will receive this signal and another antenna will receive the another satellite signal. So means we require a two antennas that will be receive the signal from this two satellite. So that is about this way we can consider that every diversity. But advantage of this means what? If supposed to be due to the sun transit or something happened to the satellite, suppose any one satellite is not work, so another satellite is there that will be used there. If any failure or a sun transit outage of one satellite, so in that case another satellite is there for the communication there. So that is about the orbit diversity. So this is about your a technique for the space diversity and orbit diversity there. And another way is about the a signal modification technique that we can use, because we say that earlier we say that we need to use the C by N ratio, improve the C by N ratio by increasing the EIRP there, so that we can increase the, or we can say that whichever the signal attenuated due to the attenuation there, so that we may be they may not be affected by increasing this C by N and the EIRP there. So another example is about, we say, another way of a signal modification. Instead of a C by N or a EIRP, we use a frequency diversity, or we can use the decreasing bandwidth, or we can say that another way we can use the adaptive error control modulation, or we can use a transmission diversity. These are about the another modification text. Earlier we say that there may be improvement in a C by N by increasing the EIRP or by increasing the gain or a transmitting power. But again, another way is about the modification of a signal is takes place. So in that case, we can use a frequency diversity. As we say that there may be a rain attenuation, and that rain attenuation is depending upon the frequency. So, so generally, satellite is work with a different band. So in that case, we need to switch the frequency of a operation when there will be a rain. If supposed to be, we say that if our satellite is work in a KU band or a C band there, So rain attenuation at this KU band will be higher, but rain attenuation at a C band will be lower there. So we can just switch the operation of a satellite from the KU band to the C band there, so that we can reduce the attenuation, rain attenuation at this particular C band. If frequency increases, the rain attenuation will be increases there. So we can reduce that rain attenuation by variation in the operation of the frequency. That is nothing but a frequency diversity there. So another way is about we can decrease the bandwidth, means we can decrease the signal bandwidth, and that will increase the C by R. Because we can say that when we decrease the signal bandwidth, so then what happened? That noise bandwidth will be reduced. Okay, whatever we can say that a noise bandwidth that will be a reduced here. Here we can say that a attenuation reduce. Attenuation, that is a rain attenuation reduce. Here the rain attenuation is reduced. Okay, if we consider that a frequency diversity, rain attenuation reduced. If we use it the decreasing bandwidth, so we can reduce the noise bandwidth. Okay, so then a adaptive error control and a modulation, and that will be used in a digital link, and that will be used to improve the bit error rate. This adaptive error control modulation that will be used only for the improving the bit error rate here. Then a time transmission time diversity. So we can say that a data transmission, when we can consider, so that transmission can be deferred when we have that, we can consider that there is no any attenuation in that particular link. Means that is called as a transmission diversity. Means what? Whenever that no attenuation in that particular region, or simply simple example, there is no attenuation, then we can transmit. Means there is no rain, then we transmit. That is nothing but a transmission time diversity. Sorry, I forgot the word time. Okay, transmission time diversity. Only we can transmit at a given particular time or that particular condition. If there is a heavy rain there, so no transmission is to be done. And then after particular, because rain will not be a continuous, that rain will be occur for a shorter duration or shorter particular period of a time. And once that rain is over, then we can transmit the signal. And that is called as the transmission time diversity. But generally, this technique is not suitable when we use the real time data or real time communication there. And these are about the signal modification technique using frequency diversity, different band of a frequency, decreasing the bandwidth, we can reduce the noise bandwidth, adaptive error control modulation, we can increase the bit error rate or performance, we can improve that BER, we can improve here. Transmission time diversity, we will use that at a different particular time there. And that is about your propagation and a propagation effects there. So now in this propagation, we have considered that whatever the changes occur in the particular signal transmission, and that is depending upon that atmospheric surrounding. Atmospheric surrounding means what? If you consider in the terms of a whatever the temperature or electron density, okay, here we consider that a characteristic or a propagation effects in the different layer. So there may be a different at different particular kilometer of a value, okay, about that at that particular altitude. So the region is there. So generally we say that a troposphere That is from the 0 kilometer to the 12 kilometer. That is about a troposphere. Then from 12 to 45 kilometer, there will be a stratosphere. Then from the 45 to 85, there will be a mesosphere. And then a 300 kilometer above 300, there will be a thermosphere. And above that 600 kilometer exosphere. Or in this particular region, we say that ionosphere, that is about a electron density. Because here, this region, we say that troposphere, there may be attenuation in that particular region. But here the electron density changes. Electron density. Because we have the different layer, that is about a D layers and a E layer. So variation in the electron density is likewise. So this is about a E layer. This is about F now. Sorry, here it is about E now. So electron density, that will be at E layer 10 to the power 4, but then it will be increased to the 10 to the power 5 or 10 to the power 6. That is about the electron. But in the case of a temperature here, we say 300, 600, 900, 1200, 1500. In this particular case, at this particular temperature, so means that temperature variation occurs at a particular kilometer. Okay, this is nothing but a temperature there. So this graph is providing you the what will be the temperature with respect to height or at that particular layer. And this again, what will be occur to this electron density? This is nothing but a electron density. Electron density. What will happen to the electron density at this particular layer? Okay. So that is about your, we say, a propagation effect. And we say that in general, we say that a ionosphere layer is about from the 50 to 2000 kilometer of but we say that D layer, E layer, and F layer, that will be in between. What we have mentioned earlier, that is about a 500 kilometer up to this. Okay, that we say. And again, we summarize that the rain attenuation, that will be more, that will be above the 10 gigahertz of a frequency. And again, it will, we say that it will be depending upon that wavelength, raindrop rate, raindrop size, or raindrop distributions, or a raindrop shapes. But it will be significant at a about 10 gigahertz. And a scintillation, we say, that is nothing but what? A rapid variation. Scintillation is nothing but the rapid variation in the attenuation. Rapid variation in the attenuation there due to the scattering irregularity. Due to the scattering irregularity. Okay, that is about a scintillation. And a depolarization, we say, that will be occur because of that differential attenuation and a phase shift. And that will be caused by the non-spherical raindrops. Okay, that is nothing but what? A differential attenuation and a phase shift occurs due to non-spherical raindrops. That's why we are getting that a cross polarization terms XPD and a isolation term. And again we say that another one is about a Faraday rotation, and that is nothing but the angular difference between the whatever the wave entering in the ionosphere and wave leaving from the ionospheric rear. Okay, that is a small variation in the angular difference. So these are about the propagation of the signal there, and now we will see a few numericals on this, and then we will just say that what will happen to the propagation effects and all other factors here. Now we can say here, we'll just type here, find the expected cloud attenuation for an uplink operating in 14 gigahertz for an earth station with an elevation angle of 30 degrees. Assume the columnar content, assume the columnar content of water as 0.5 kg per meter square and temperature as 10 degrees Celsius. Now our aim is about to find the cloud attenuation. So here a specific attenuation constant is given for this 14 gigahertz of a frequency, and that will be of a 0.15. Now our aim is about to find out the cloud attenuation. So that is about a total cloud attenuation is equal to, that is about a length, or we can say that what will be the content of the water content is present. We have a columnar content in the water, that is about L into Kc divided by sine of theta. This is about a L is nothing but a columnar content of water. This one is nothing but what we have a specific attenuation. Specific attenuation here. Then that theta is nothing but the elevation angle. Now this total constant, you can say that it total cloud attenuation, that AT, that will be is equal to what? L is a zero point 0.5, it is given. 0.5 kg is given now. Here is about the elevation angle is about a 30 degree. And we have the operating frequency is about a 4 gigahertz there. 14 gigahertz. And temperature is given is about a 10 degree. So now AT is equal to what? 0.5 into Kc. Kc is what? A 0.15. And sine of theta, theta is about a 30 degrees given. So after solving, we'll get that AT is equal to 0.15 dB. Okay, that is nothing but a total cloud attenuation. Then next about an earth station. An earth station receives an earth station receives a signal from The satellite, a Earth station receive the signal from the satellite in 11 gigahertz. The rain rate in the area of the Earth station is 20 mm per hour. Find the specific attenuation. Find find the specific attenuation of the rain volume. Find the specific attenuation of the rain volume. Now here we consider that. So we have that the frequency is about 11 gigahertz. So for that 11 gigahertz, we need to calculate that a small a and a small b. That small a and a small b means what? Because our equation of attenuation, that alpha is equal to what? A into r raised to b, that is a dB per kilometer. So a at 11 gigahertz is equal to what? 4.21 into 10 to the power minus 5 f raised to 2.42. F is a 11 gigahertz, so we will get that 0.01395. This one f, you can put that f is equal to 11 gigahertz here. So we will get that a here. Similarly, we can calculate that b. B is equal to what? 1.41 into f raised to minus 0.0779. You can put that f is equal to 11 gigahertz. You will get that 1.17. So alpha is equal to a. A is what? 0.01395 and B is what? 1.117. Now that area of the earth station is about a, the rain rate in the area of the earth station is about a 20 mm per hour. Means R is about a 20 mm per hour. So that's why A is what? 0.031 sorry 0.01395 into R is about a 20 and B is about a 1.17. And if you solve it, this one is A, this one is a B here. This one is a B, this one is a A. So here we have the A, here we have the B, and this one is a R. R is about a 20. This one is about a R. R is about 20. So we'll get that alpha. Alpha is equal to what? That is the specific attenuation 0.464 dB per kilometer. That is about the alpha here. Next one, the elevation angle for a geosatellite the elevation angle for a geosatellite at an earth station is 40 degree. The earth station is situated at an altitude of 500 meter above the sea level. The stratified height for the specific attenuation of 1.8 dB per kilometer. Now for this we need to consider that here we need to find out what will be the path length. So path length is L. Okay, this one is about a path length. We say it is nothing but a L. L is equal to what? What will be the height from the bottom or a sea level to the freezing point HR minus, or you can say that is about HR is nothing but the height of a rain minus H0 by sine of theta. Theta is nothing but the elevation. So this one we say elevation, that H0 is nothing but a altitude, and this HR, this one is about HR, is nothing but that height of the rain, height of the rain column. Means what? We have the Earth station here. This one is about a Earth station we say. It transmit the signal, and here is somewhat we have the freezing point. Okay, we have somewhat a freezing point here, and it transmit the signal, that is nothing but a path here. This one we say it is nothing but a path, or we can say that is about the effective length L here. And from this is about a bottom here or sea level. This one is about a freezing point. So this one is about a HR here. And Earth station is located. We have some. This one is about the Earth station ground with respect to that sea level. That is nothing but a HO here. And this is about the elevation angle, that is about a theta. So now our aim is about to find out a path length through this rain. This is nothing but a rain here. We have the rain here. Okay, in this particular region. So that is about a L. L is equal to HR minus H0 divided by sine of theta. So HR is what? That is a specified height of a rain from the sea level. So it is nothing but a 2.5 kilometer. This one is the HR is about a 2.5 kilometer. Now, a altitude is given, that is altitude of a 500 meter. So that is a H0. But we need to consider that high height in terms of a kilometer. So that's why H0 is equal to 0.5 kilometer. So we can write that a HR is equal to what? That is a 2.5 kilometer, and H0 is equal to zero point 0.5 kilometer. And a elevation angle, that theta is a 40 degree. So we can say that theta is equal to 40 degree. So we can put here L is equal to 2.5 k minus zero point 0.5 divided by sine of 40. That will give us the value 3.11 kilometer. That is about the length. Then a specific attenuation we need to find out B point, that is about a path attenuation for a specific attenuation of a 1.8 dB per kilometer. So for a given specific attenuation 1.8 dB per kilometer, so path attenuation A is equal to what? Alpha into L. That alpha is equal to 1.8 is given. Into that length we obtain, that is 3.11 above here. So we'll get that A is equal to what? A 5.6. That is about a dB. And that will be the attenuation there. Next about a two orthogonally polarized waves have electrical field vector electrical field vector of amplitudes 5 and 3 volt per meter in vertical and horizontal direction respectively. These waves are rotated by 5 degree in the atmosphere. Find the cross polarization. Find the cross polarization discrimination between. Find the cross polarization discrimination between the field vector. Now here the two orthogonally polarized waves have electrical field vectors of amplitude 5 and 3 volt per meter in vertical and a horizontal direction respectively. These waves are rotated by 5 degree in the atmosphere. Find the cross polarization discrimination between the field vectors. Again, find the isolation between the copolar and, or you can say copolarized, and a cross polarized component. Now our aim is about to find out that XPD1 is equal to 20 log of E11 by E12. XPD1. So XPD2, that is cross polarization term 2, 20 log of E22 by E21. Now in this statement, if you see that another factor, that is isolation, we need to find out. Now if you see the statement here, that field vector, electrical field vectors of amplitude 5 and 3 in vertical and horizontal. Now this one is about a vertical component, we say it is about E1, and this one is about a horizontal component, that is about the E2 now. Means we have the vertical component of a E1 here and horizontal component E2. And these waves are rotated by 5 degree. These waves are rotated by the 5 degree. So means for a given particular field component, suppose I draw here for the E1 and the E2. So for the E1, because this one is rotated by a 5 degree. So we can say this one is about E1 now. And this one we say from this E1 we'll get that one vertical component that will be E11 and another component we are getting that will be the E12. Now the another component that will be a E2 here, and from that we'll get that a component a E22 and we'll get the component that will be a E21. Means we can draw a circle for this particular component and we draw the another circle for this particular component. So if you see that E1, we have the E11 and E12. For the E2, we are getting the E22 and E22. So from this, we can calculate that the E11 is equal to what? A E1. This because this one is a theta here, cos of theta, and that will be E1 cos of theta. That E1 is what? It is a 5 cos of theta, that is about a 5 degree. So we'll get that E11 is equal to 4.98. Next about the E12. E12 is equal to what? E1, because theta is here cos, so it is nothing but a sine. So E1 sine of theta is equal to what? 5 sine of 5 is equal to 0.436 E12. So E22 is equal to what? This is E22 is equal to what? This is the theta here. So E2 cos of theta, it is 3 cos of 5 is equal to 2.988. Then E21, that is opposite. So it is nothing but what? E21 is nothing but E2 sine of theta. E2 sine of theta is equal to 3 into sine of 5. So it will give us that E21 is equal to 0.262. If you put that here, 20 log of E11, that is 4.98 by 0.436, you will get a 21.15 dB. If you put here 20 log of E2 to here, so 20 log of 2.988 divided by 0.262, you will get that 21.142. Similarly, we can calculate that isolation I1 is equal to 20 log of E11 by E21 is equal to 20 log of 4.98 divided by 0.262 is equal to 25.6. I2 is equal to what? 20 log of E22 divided by E12 is equal to 20 log of 2.988 divided by 0.436 is equal to 17.72 dB. Okay, so this E11, this E1 It makes an angle theta that is about a 5 degree. So E1 has E1 1 and E1 2. E1 1 is equal to what? That is E1 1 is equal to E1 cos of theta, and E1 2 is equal to what? A E1 sine of theta. This theta. Okay. Then for this E2, E2 2 and a E2 1. So E2 has E2 1 and E2 2. So this E2 2 it belongs to this particular theta. So that's why E2 2 is equal to E2 into cos of theta, and E2 1 is equal to what? E2 of sine of theta. So you will we have calculated that E1 1, E1 2, E2 2, and E2 1, and we have put that all the values in cross discrimination factor XPD 1, XPD 2. We'll get that 21.15 dB and 21.142 dB. Similarly, for the isolation, 25.6 dB and 17.72 dB. That's all.